Hi. In this problem, we're going to explore an alternative way of calculating expected values for a special class of random variables. And the class of random variables we're going to consider in this problem are those that take on only non-negative integer values. So the random variable x can only take on values 0, 1, 2, 3, 4, and so on. And so first let's recall what the standard definition of expected value is. The expected value of a discrete random variable x is just a weighted sum. So you take all possible values that the random variable can take on. So we'll sum k from negative infinity to infinity, and we'll weight the value that it can take on by the probability that the random variable actually takes on that particular value. So this is the PMF, evaluated at some value k, and that's the weight applied to that value. And we can simplify this formula a little bit if we consider only non-negative integer random variables that can take on only non-negative integer values. So we can actually wipe out everything from negative infinity to 0 because, or negative infinity to negative 1 because the random variable can take on those values. And we can also discard the case where k equals 0 because when k equals 0, this expression is 0, so it doesn't add anything. Okay. What we want to do now is to show in this problem that there's an alternative way of calculating the expected value when you have a non-negative integer valued random variable. And that is given by this alternative summation. So you're also summing k from 1 to infinity, but now you're actually summing some probabilities. And we call these things tail probabilities because it's a probability that the random variable is at least some value. So imagine that you have a PMF, and you take a k value, and this will take everything to the right of that k value. So you can imagine that this is some sort of tail of the distribution. And now you sum this from k equals 1 to infinity, and as it turns out, as we'll show very soon, these two actually give you the same value for this class of random variables. All right, so let's actually get started and do that. So part A is to show that this is true. Okay, so let's write out again what it is that we're trying to show. So we're trying to show that this somehow will give you the same expression as this summation. All right, so, well, the only thing we can really do here is try to substitute in what this probability, this tail probability is. Well, what is this tail probability? It's just adding up probabilities in the tail. And so we can actually write this probability as a sum of I from k to infinity of the PMF of x evaluated at I. So this probability is equivalent to this. All we're doing is just writing a different way. This is just the same as adding up probabilities from k onwards, and this is the same as adding up probabilities from k onwards. All right, so now we have something that is starting to look more like this. We at least have a PMF of x involved, but it still has a double summation, and it's missing some k's. So let's see how we can resolve that. Well, as the problem gives you a hint to try exchanging the order of these summations. So right now we're summing k first and then I. All right, so but we have to be a little bit careful because we can't just swap these and call it a day because we have to be a little bit more careful. So let's actually go here now to this plot and see how we actually interchange these summations. So what we're really doing is, as we currently have it set up, first the outer summation increments k from 1 to infinity. So I have k here, so it goes like this. And then the inner summation goes from k to infinity. So let's just see exactly what values of k and I we're summing here. So for k equals 1, we sum from I equals 1 to infinity. So it's really summing up everything like this way, going up vertically. And then once that's done, you come out to the outer summation again, you increment k to 2, and then you sum I from 2 to infinity. So k goes to 2, and then you sum I from 2 to infinity. And then k goes to 3, and you sum from I equals 3 to infinity, and so on. Right? So what you see is that really we're just covering all these points in this kind of upper triangular portion of this grid. Now, in order to change summations, what we're effectively doing is instead of summing things vertically like this, we're going to sum things horizontally. So I now becomes the outer summation, and k becomes the inner summation. So how do we do this? Well, for each I, like let's say for I equals 1, we'll take, well, there's only one value, so k is 1. For I equals 2, we'll take k from 1 to 2 to this diagonal. For I equals 3, we'll take k from 1 to 3 to this diagonal, and so on. So now, instead of summing vertically, we'll sum horizontally across. And what that amounts to, using symbols, is we sum I from 1 to infinity now, and the inside we sum k from 1 to I. And the thing that we're summing still stays the same. So again, let's just try to verify that this is correct. So for I equals 1, you sum from k equals 1 to 1. So you pick up this 1 point. For I equals 2, you sum from k equals 1 to 2. So you pick up these 2. For I equals 3, you sum from k equals 1 to 3, and you pick up these, and then so on. So it looks like we have it correct. Now we've interchanged the summation, and it turns out that this helps because if you, we can now actually simplify what this inner summation is. So if you notice, the thing that you're summing over is k, but what you're summing doesn't involve k at all. And so what you're doing is you're just summing lots of copies of the same thing, of the same value. And in particular, you're summing from k equals 1 to I, so you have I copies of the same thing. So this inner summation actually simplifies to just I copies of what you're summing, which is this. And now we are basically done, because if we compare these two, we see that they are effectively the same. The only difference is that here we're using k as the variable that we're summing over, and here we're using I, but really it's the same thing. So what we've done here in part A is to show that, in fact, this is correct. This is actually an alternative way of calculating expectations for this class of random variables. All right, and the trick here really was to write things out and then do a clever change of summation. All right, so why is this useful? Well, it could be the case that depending on how the random variable is defined, maybe this way of calculating the expectation is easier than this way of calculating the expectation. And so it's useful to have multiple ways of attacking the same problem. All right, so now let's move on to part B, where we actually will try to exercise this new formula on a particular random variable. So let me erase this part. And the random variable that we're dealing with is random variable y. And we're told that the PMF is 1 over b minus a plus 1 when y is a through b. All right. And our a and b are integers. Okay, so what we have is it takes on some value for some range of y's from a to b. And a and b are integers, and they're non-negative. So what we see is that y is, in fact, one of these types of random variables that we're talking about in this problem. All right, so the question is, what is the expected value of this random variable? And now let's, instead of using the kind of standard way of calculating it, let's use this new formula just to get some exercise. All right, so the thing that we need to do is calculate what these tail probabilities are. So let's actually calculate that. So what is the probability that y is at least some k? Well, it turns out that this depends on what k is. And in fact, there will be three different regimes. And it might actually be helpful if we draw out what this PMF kind of looks like. So it goes from A to B. And the PMF is given by this 1 over b minus a plus 1. But notice that this is just a constant with respect to y. It doesn't actually depend on what y is. And so what we have really is actually just a uniform distribution. So everything is height 1 over b minus a plus 1. All right, so let's think about the three different regimes. Well, if k is, say, less than or equal to a, then the probability that the random variable is greater than or equal to k, well, that covers the entire PMF, right? And so by definition, that has to sum up to 1. So we know that when k is less than or equal to a, this tail probability is just 1. And the other simple case is when k is greater than b. So when it's out here, well, there's no more PMF to the right of k. And so when it's all the way out here, the tail probability is just going to be 0. So when k is at least b plus 1, it's 0. And the interesting regime is really when it's in the middle. So when k is between a and b. So let's just plop down a k somewhere. Well, in order to calculate this tail probability, we just have to calculate how many of these kind of sticks are there that cover that go from k to b. Well, let's just pretend that, say, this is k. Well, how many of these PMFs are there? There are b minus k plus 1 of them, and each one contributes 1 over b minus a plus 1, so it's b minus a plus 1. All right, and so now we have the tail probabilities in all the three different regimes. And what we have to do now is just sum over all the possible k's, and that will give us the answer. And so let's finish up that last step. So the expectation of y is just the sum of all of these. So let's break things up into the different regimes. So for when k is between 1 and a, this tail probability is 1, right? So we just have k equals from 1 to a, you just sum up 1s. And then when k is between a plus 1 and b, you get this thing. So we'll plug that in, b minus k plus 1 over b minus a plus 1. And then when k is greater than b, you get 0. So we don't even have to include that anymore. All right, and so now the rest of it is just algebra. The first term is easy. There's just a copies of 1, so you just get an a. And this, we can just do some more algebra and simplify things out. And what we get is that this sum actually ends up being b minus a over 2. So which, when we combine, we get that this is just b plus a over 2. Becomes our final answer. And do we trust that this is actually correct? Well, we can pretty easily verify it in this case because random variable, as we already noted, was actually uniform between a and b. And so we know that for a uniform random variable, the expected value is just the midpoint, which is exactly b plus a over 2. OK, so to summarize this problem, we've shown that for a certain type of random variables, you have an alternative way of calculating expectations, which may, in some cases, be easier than using the standard definition. And then we've applied that to a specific case of a random variable. And this also gave us a good opportunity to practice, get some more practice calculating out probabilities and working PMFs and expectations. All right, so see you next time.